Hi friends! So today we're back with the fundamental theorem of calculus part 2, sometimes called the integral evaluation theorem. So this theorem says that if f is continuous at every point in a closed interval from a to b, and if big F is the antiderivative of little f on that interval, then the integral from a to b of little f of x dx is equal to big F of b minus big F of a. This says that any definite integral of any continuous function f can be calculated, so long as the antiderivative of f can be found. So let's take a look at a few examples. So the first one says, I want to determine the antiderivatives of the following functions. So notice in the beginning, we're not going to be actually taking any integrals. We're just going to be finding antiderivatives. So for f of x equals x cubed, the antiderivative, big F of x, let's work backwards. In order to get an x cubed, when I take an antiderivative, I would need to start with an x to the fourth. And then think about your power rule. When you take the derivative, the 4 would come down in front, so you'd have the 4x cubed. So I need to figure out how to undo that 4. And so what I need here is a 1/4. You can easily check behind yourself by taking f prime of x, which would be 4 times 1/4 x cubed, which would just be x cubed, check. Let's take a look at the next one. In the next example, I have f of x equals x raised to the negative fourth. So now when I'm finding the antiderivative, big F of x, what I'm going to do is I'm going to add 1 to that negative 4, because I know when I take the derivative, I'll end up bringing down that negative 3x, and then I would subtract 1 from the negative 3 to have a negative 4 up there. So now what I need to do is need to figure out what constant is out there so that when I bring down that negative 3, it cancels out, so I only end up with a 1 as my coefficient. And so that would need to be a 1 over a negative 3 or a negative 1/3. And you can easily check behind yourself by calculating f prime of x. Then I'd have negative 3 times 1 over negative 3. Then you'd have x raised to the negative 4. So you can see here, these would cancel to just be a 1, x to the negative 4. So this indeed is the antiderivative of little f of x. Let's do one more. So I have f of x equals x to the fifth. So I have big F of x equals, so I need to think about what should x be raised to in order for me to take the derivative and get an x to the fifth. And it would need to be x to the sixth. And then I need to think about what needs to be out front in order for me to just have a 1 as my coefficient. And that would be a 1/6. And I can easily check behind myself by calculating big F prime of x. I would get 6 times 1/6, and then x would be raised to the fifth, giving me x to the fifth when I simplify. So that is the antiderivative. So now that you have done these 3 examples, I want you to think about what if you have f of x equals x to the r, such that r is some real number, and I'm going to say r is not equal to 1, r is not equal to 0. So some real number, not 1 or not 0. Then my antiderivative, if I'm thinking about a potential pattern for f of x, I think it was going to be equal to your x is raised to the r plus 1, and then what you would do is you'd have a 1 over r plus 1 out front, if you were kind of coming up with a general rule. You might see this written as x to the r plus 1 all over r plus 1. So that would be a more general rule. What do you think about f of x equals k, such that k is just a real number, it's just some constant? Well, there, big F of x, the antiderivative, is just going to be k times x, because I know when I take the derivative of kx, I would just have k. So that would be the antiderivative. What about f of x equals 1 over x? Well, I noticed that right there. I noticed that that is the derivative of natural log of x. So the antiderivative is going to be natural log of x. But wait, I'm thinking about when I move in this direction, so if I have the function, let's use g. Let's say g of x equals natural log of x. Notice that the domain of g of x is only from 0 to infinity. So when I go to my derivative, g prime of x, it is equal to 1 over x, and that domain is still only from 0 to infinity because the domain I was starting with was only from 0 to infinity because of that natural log function. When I'm going in the opposite way, the domain of this function, 1 over x, is all real numbers such that x cannot be equal to 0. So when I am going to my antiderivative, I have this natural log function, but I actually can't plug in negative values to the natural log function because those don't return real numbers. So what I need to do is I need to adjust this antiderivative so that I can still plug in all of the values right here from my little f of x into my antiderivative. And this is actually a pretty easy fix. I'm going to change these to absolute value signs right here. So my antiderivative, let me grab a pen, not a highlighter, f of x is actually going to be the natural log of the absolute value of x. We got to be careful about that domain. All right, the next one, I have f of x equals 7 raised to an x. So let's recall the derivative of a constant raised to an x is equal to the constant raised to the x times the natural log of that constant. So think about going backwards. Look at what both things have in common. So we need to go backwards. All I have is that constant 7 raised to an x. So the antiderivative looks like it's going to be the 7 raised to an x. And then I need to undo that natural log of 7 on that multiplication. So I'm going to end up dividing by that natural log of 7. Next, let's take a look at the next example. F of x equals e to the x. This one's easy because the derivative of e to the x is e to the x. It's going backwards. The antiderivative of e to the x is e to the x. Let's consider what if I have f of x equals e raised to the k times x, such that is a real number. K is a real number. So remember, k is just going to be a constant here. So my antiderivative will also be e raised to the k times x. But I know when I take the derivative, you would be multiplying by that k, so I'd have to undo that. So I'd need to multiply by a 1 over k in order to undo that k. More commonly, this will be written as 1 over k e to the kx, or maybe it's even written as e to the kx over a k. So there's the antiderivative. Looks like next we're getting into some trig. So I have f of x equals sine x. So the antiderivative, what would give me a derivative of sine? And that would be negative cosine of x. Let's look at the next one, cosine x. So I have f of x equals cosine x. The antiderivative, what would give me a derivative of cosine of x? Well, that's easy. That's just sine of x. Next, f of x equals secant x, tangent x. So what has a derivative of secant tangent? It's just secant of x. Let's take a look at the next one. So I have f of x equals 1 over 1 plus x squared. You may not recognize this one. It's not super common, but I do think back hard. Definitely learned it back when we were learning derivatives. This is the derivative of the arctan function, or tangent inverse. So the antiderivative is tan inverse of x, or arctan of x. The next one, f of x equals negative cosecant squared x. I recognize that as well. What has a derivative of negative cosecant squared is cotangent of x. All right, the next one, f of x equals the square root of x. It's going to help me if I rewrite this as x raised to the 1/2. And then I'm just going to be using that rule that I developed earlier in part D. So antiderivative is going to be x raised to the 1/2 plus 1. I need to add 1 here, giving me a 3/2. And then out front, I'm going to have 1 over 3/2. So when I simplify this, I get 2/3 x to the 3/2. And that would be the antiderivative. All right, let's look at p. F of x equals the cube root of x. Well, that's x raised to the 1/3. So my antiderivative is going to be x raised to the 1/3 plus 1. So I'm going to add 1 there, and I'd get 4/3. And then I'd have 1 over 4/3 out front. So that'll be 3/4 x to the 4/3. So in this first section, we were just finding antiderivatives based on derivative rules that I learned back in chapter 3. One thing that I want to point out with all of these antiderivatives, every single one we just did, whenever I'm taking an antiderivative, we need to remember that there always might be some constant floating out here. So if I have f of x equals 1/4 x to the 4th, when I take the derivative of that, I will get x cubed. But there might be some constant sitting out there, a plus a 2, plus a pi, plus a e, plus, 7 million, who knows. But you could have a constant out here, and it could literally be any constant, and the derivative of it would be 0. So we need to account for that as I'm going through and taking an antiderivative. So for all of these, I need to tack on a plus c for every single one, because there could be a constant out there at the back, and when I take the derivative of it, it would be a 0. Handful more. All right, now I feel good about all of those antiderivatives. So now that we've got some practice with antiderivatives, we are going to start to evaluate integrals using part 2 of the fundamental theorem of calculus. So up until this point, we really haven't been able to evaluate any integral because not all functions have geometric shapes that I can use to find the area under the curve, like the ones we're getting ready to do. But now that I have that second fundamental theorem of calculus, I will be able to evaluate any integral so long as I can find the antiderivative. So the first one example says, evaluate the integral from 1 to 2 of x to the 4th. I'm going to make this a little bit bigger. So what I need to do is I need to find the antiderivative of x to the 4th. So that will be x to the 5th, and then I need to have a 1/5 out front. And what I'm going to do is I'm going to evaluate the antiderivative from 1 to 2. So this here is my evaluation bar. And what the fundamental theorem says I can do is that once I have the antiderivative, I will plug in the upper limit of integration and then subtract the evaluation at the lower limit of integration. So in my rule, this would be f of b minus big F of a. And here, this right here, is big F of x, the antiderivative of my integrand, x to the 4th. All right, so now we can evaluate. I will have 1/5, 2 to the 5th is 32, minus 1/5, and 1 to the 5th is 1. I have 32/5 minus a 5th, which is 31/5. So if we were to draw this out, this picture, the function x to the 4th kind of looks like a quadratic, but it's skinnier. I know that it's going through the point 1, 1, and it's going through the point 2, 16. So what we just calculated is that the area under the curve from 1 to 2, this area right here, is equal to 31/5. And I know that it's just the area. This is equal to the area because x to the 4th is a positive function over the interval from 1 to 2. Let's look at another example. I want to do the integral from 0 to 4 pi over 3 of sine of x. So, first things first, and I should have done this on the last one too, I need to make sure that the integrand sine of x is continuous over the interval from 0 to 4 pi over 3, which it is, but I definitely should be checking that every time. So this will be equal to the antiderivative of sine of x, which is negative cosine of x, evaluated from 0 to 4 pi over 3. So now I will plug in my upper limit of integration, subtract, plugging in my lower limit of integration. So cosine of 4 pi over 3 is equal to negative 1/2. Minus the negative cancels out. I'm just going to put this plus sign. And cosine of 0 is just 1. So I end up with negative 1/2, which is 1/2 plus 1, which is 3/2. So let's draw a graph of what we just found. So sine of x looks like this. We'll go one more. All right. So this is what a sine function looks like. And we were asked to do the integral from 0 to 4 pi over 3. So remember, 4 pi over 3 is probably like right here. Because on my unit circle, four pi over 3 is about here. All right. So what you just found was, if I were to take the area above the curve, so all of this blue area, minus the area below the curve, you would have 3/2 of a unit, so 1.5 units. And then also, I guess, how did I evaluate cosine of 4 pi over 3 really quickly? Some of you might be unit circle memorizers, and that's fine. I'm not. But I am a triangle memorizer, so I always know this triangle. The reference angle of 4 pi over 3 is just pi over 3. And then the definition of cosine is going to be adjacent over hypotenuse, so 1/2. And I know that cosine in the third quadrant here, in quadrant 3, cosine is negative. So that's why I knew this was negative 1/2. 1/2 I got from my triangle, the negative I got from knowing that cosine is negative in the third quadrant. Just a little review if you needed it. All right, let's look at a couple more examples. I've got 6 total examples to do. All right, so the next one I have the integral of 1 to 5 of 1 over x plus x. So I have the antiderivative first of 1 over x is natural log of the absolute value of x. Don't forget the absolute value. Plus the antiderivative of x is 1/2 x squared. And I'm going to be evaluating this from 1 to 5. So parentheses are going to be my friend here. I'm going to plug in 5. I'll have the natural log of the absolute value of 5 plus 1/2 5 squared minus the natural log of the absolute value of 1 plus 1/2 times 1 squared. And then I'm going to start cleaning this up. So the absolute value of 5 is just 5, so I'll have natural log of 5 plus 25 halves minus natural log of 1 is just 0, and then 1/2 times a 1 squared is just a half. So I'll end up with natural log of 5 plus 24 halves, which is just 12. So I have natural log of 5 plus 12. Not too bad. Why don't you pause the video and do this next one on your own, and then come back when you're ready. Okay, so here I need to figure out the antiderivative of 2x. So I know that I'm going to need an x squared, and notice that when I take the derivative of x squared, the 2 would come down and I would just get the 2x to the first. So the antiderivative of 2x is just x squared. The antiderivative of 5 is just 5x. I'm going to evaluate this from -3 to 4. So now I'm going to plug in the 4, so I'll have 4 squared minus 5 times 4 minus, plug in the -3, I'll have -3 squared minus 5 times -3. So 4 squared is 16, minus 5 times 4 is 20, minus -3 squared is a positive 9, minus 5 times -3 is a positive 15. So I end up with a -4 minus a 24, giving me a -28. All right, let's look at the next example. All right, so I have the integral from -4 to 0 of e to the 3x minus 1/5 x cubed. So let's first tackle this antiderivative. So the antiderivative of e to the 3x is going to be e to the 3x, but then I need to undo that constant, because when I take the derivative, I would multiply by a 3. So to undo that multiplication of 3, I would multiply by a third. Next, I have this 1/5 hanging out, and I would end up with an x to the 4th in order to get that x to the 3rd. So I need to multiply by something there that's going to give me a 1/5 out front, and I believe 1/4 is going to do it. Let's just go backwards quickly. I have 1/3 e to the 3x minus, this becomes a 1/20th x to the 4th. I need the eraser. So think about going backwards. When I pull that 4 down, I'd have 4/20ths, which is indeed a 1/5, times x to the 5th, or x to the 4th. And that 4th would become a 3 when I take the derivative. So I need to evaluate this from -4 to 0. So let's plug in 0 first, my upper limit. And now let's plug in the -4. Oops, I don't want to put the negative. I was trying to work ahead a little bit, but I don't want to. I want to show every step. All right. So here I have this term just going to 0 altogether. And then e to the 0 is a 1. So 1/3 times 1 is just 1/3. So then I have minus 1/3 e to the -12, and then minus 1/20th, and then -4 to the 4th, 256. So now what I need to do is I've got the 1/3, and then I need to make sure I distribute my negative. So I'll have 1/3e to the 12th. And then when I simplify this, I get minus plus, just kidding, 256/20. So I end up with 1/3 minus 1/3e to the 12th. and 256 over 20 becomes a 64 over 5. So I could get a common denominator if I wanted to, but I think I'll just call it a day because that is algebraically sound. All right, so I've got one more example to do. Example 6. I want to do the integral from 1 to 16 of the square root of x dx. So first, I think it'll be good if we rewrite that x to the, or the square root of x as x to the 1/2 dx. It's going to help me take the antiderivative. So for my antiderivative, I need to add 1 to that 1/2, so I'd have x to the 3/2. And then in the front, I'll have 1 over 3/2, which is 2/3. And then I need to evaluate that from 1 to 16. All right, so next I'll have 2/3, plug in the 16, my upper limit of integration, minus 2/3 times 1 to the 3/2. So now when I evaluate this, I'm going to come off to the side. 16 to the 3/2 is the same thing as the square root of 16 cubed. So I'll end up with 4 cubed, which is 64. So this will be 2/3 times 64 minus 2/3 times 1, which is just a 1. Cleaning this up, I notice I have a 2/3, so I'll be able to factor that out. And I'd have 64 minus 1, which would be 2/3 times 63. And now the 3 and the 63 will cancel, giving me a 21. So I'll have 2 times 21, which is just a 42. Easy enough. I do want to point out that here, because I have that constant, I could say this is equal to 2/3 times x to the 3/2 evaluated from 1 to 16. And that's totally fine if you do that, because it distributes right back in. So I'd have 16 to the 3/2 minus 1 to the 3/2. So I'd have 2/3. 16 to the 3/2 is 64, minus 1 to the 3/2 is 1. So notice you end up right here. I don't think it's that big of a deal for this example, but it could be depending on what that constant is. So you can certainly pull out the constant and factor it back in later. All right, so now you are all set to work on these homework problems on page 303 on the fundamental theorem of calculus part 2. Have fun!